Hello, everyone. Welcome to our ANM Pathways webinar, Quantum Computing with Troy Baietto from ANM, Solution Architect. In today's session, we'll be sharing details about our next webinar, so hold on to that. Before we dive in, I'd like to take a few seconds for a few housekeeping items. In today's webinar, it will be recorded. We'll send you the link after the session so you can rewatch the content or share with your colleagues. We encourage any questions and comments throughout the webinar, so please use the chat button at the bottom of your screen. We'll be taking a look at that throughout the webinar itself. And now I'd like to introduce today's presenter, Troy Baietto, Solution Architect at ANM. The floor is yours.
Appreciate it. Thank you, Amanda. And hello, everybody. Welcome to our webinar on quantum computing. My name is Troy Baietto. As Amanda mentioned, I'm a solutions architect here in A&M, coming to you from our Scottsdale, Arizona office. We wanted to make sure that we got in front of this topic. I know it's come up a few times with some of our customers. It's very early, but we wanted to make sure that you guys had the education and sort of the market realities of quantum computing, especially in cryptography and security. One of the things that I've faced when I was my last IT job was, executives and non-IT people hearing something from a podcast or on TikTok or something about some IT technology that's up and coming that that person would walk into the IT room or the cubicle area and say, hey, what about AI? What about this next big thing? When do we get in front of 3 televisions and things like that? Sometimes they work out and they become the next big thing, and sometimes they don't. So we want to make sure that we're in front of this. And so, why quantum computing? Obviously A&M as a technology consultant, we want to be in front of anything that is that could become a surprise to our customers. So we want to make sure that we're removing the surprises and getting in front of things and researching some of the emerging technologies and some of the trends. So that you guys don't have to. So quantum computing has become it's starting to become a big topic. We believe that this year, sort of next year, it's going to become more and more of a talking point, especially for vendors and for a lot of federal and government agencies. And you can kind of see on the screen here, obviously there is a lot of government organizations that are getting in front of this and advising their constituents on how to defend against some of the things that quantum computing is going to challenge us with. And so some of it is very, very new. For example, that executive order you'll see there. But personally, for me, one of the reasons why I brought up this topic and why I volunteered to talk about it was I've always been a big fan of Albert Einstein, and even Albert Einstein mentioned he didn't really understand quantum mechanics. It was something that didn't work out with his theory of relativity, and he called it spooky actions at a distance. So I was always, I thought it was always really cool, the really smart guy, and at the end there was always something that he was trying to work out to figure this last piece into it for him. So by the end of this, we're all going to be thoroughly confused about quantum mechanics and quantum computing. But the idea is that you guys come away with what is the impact from IT and infrastructure and cybersecurity perspective, and what is sort of just the hype and the fun nerd stuff. How do we separate that? So from an agenda perspective, we'll talk real quick about what are the basics. How do quantum computers work? What are they good for? What are their applications? The reality is, the reason we're talking about this is the impact on cybersecurity. It is a really cool technology, but one of the things that has come out early in this technology is the impact of cybersecurity. So we'll talk about that. We'll explain some of the standards and frameworks that are already out there and some of that are up and coming. What are some of how do you work with vendors? What are they doing? And then a call to attention, not really a call to action. Again, this is very new technology. There's a lot of things that can be planned for, but really not a lot to as far as you're not going to walk away saying, hey, we need to move right now. Obviously, this is something that vendors will be talking about, your supply chain will be talking about, and anybody in cybersecurity is looking at this as well. So on the right there, you'll see that is actually a picture of a quantum computer. You can kind of see, back in the day with classical computing, they took up a whole room, and everyone was like, "Oh, these computers, no one's going to ever own one. It's never going to be a thing." Quantum computers today are very much like the original sort of large room scale computers. So you can see they kind of look like chandeliers. They are very, very sensitive to outside forces. So any noise, any vibrations, anything like that really mess up the computations and the ability to experiment with these quantum computers, which is why you see it hanging from the ceiling. They're able to do better vibration isolation and noise isolation if it hangs from the ceiling. The other thing is for most quantum computers, they have to operate in deep space temperatures because we're manipulating things in the quantum realm, quote unquote, to use the Ant-Man Marvel Entertainment word. Even energy from temperature can be a bad thing. So that's why the chip lives at the very bottom of that chandelier, and all the rest of it basically is to cool it down to very, very low, 4 Kelvin and below temperature, so that the computations can work, right? So real quick, we're going to touch on this real fast. I don't want to get too far into this because this is just a lot of physics and science. But I think it's important to understand, as you're working with vendors, as you're working with other people that are talking about a post-quantum computing world, which is PQC, which is what a lot of vendors are talking about coming up. It's good to know what are the difference between classical computing that we know today and quantum computing. So classical computing, we all know, zeros and ones for computation. If there's voltage, it's a 1. If there's no voltage, it's a 0. And we use logic gates in order to create computations and manipulate those zeros and ones so that we get a result. Those logic gates are built within transistors, and the more transistors we get on a wafer, the faster the processor. So that's why you've seen computers go from the size of a room down to the size of our cell phones. I think everyone kind of knows that evolution of classical computing. So it's been fun to watch, all that stuff in my lifetime, and then growing up in IT and watching the classical computing just get faster and better. The quantum computing piece of it is a little different. So instead of using bits, we use what we call quantum bits or qubits. Qubits can be a 0 or a 1 or a combination of both. So that's where things get a little fuzzy, is having multiple states at one time. And those multiple qubits can combine, they can represent multiple possibilities at once. We'll talk about what that means and why that creates such an opportunity for quantum computers to do certain things. But before we do that, let's really quick dive into a quick analogy on traditional versus quantum computing. Again, only 2 states in traditional bits, 0 and 1. It's kind of like a coin. It's either heads or it's tails. The state's easily read. We know it's either a 0 or a 1. There's really not much to it. It's either heads or tails. You flip that coin, and you'll get a result at the end. Quantum bits are a lot like a spinning coin. So they exist as heads and tails at the same time. So if you take a coin, put it on a table, and spin it as fast as you can't really say, is it heads or tails? You can argue that it's both. And so you don't know until you smack the coin and push it on the table. We'll talk a little bit about what that means. But once you smack it on the table, then you'll get a 0 and 1. Otherwise, it exists as both heads and tails. Again, this is kind of very fuzzy logic. It's hard to kind of, the more I dived into this piece, the more confused I got. So it's not super important. But even folks that come away with a master's degree in physics still have a hard time understanding exactly how something can be in multiple states at once. So one of the things that, from a concept perspective, that multiple states at once is called superposition. So when you read about quantum computing, post-quantum computing in cybersecurity, you'll see superposition. Again, that's the ability for that qubit to exist in multiple states at once. If you're familiar with the thought exercise of Schrodinger's cat, it's in a box, but the box is closed. Is it dead or is it alive? It's both, right? Until we observe that. And so entanglement is something that I was really intrigued at. You can basically take a particle like a photon and clone it or entangle it with another photon. And the weird thing is, and this is what Einstein couldn't wrap his head around, is if you take one of those photons and put it on the other side of the galaxy and wiggle one, the other one wiggles at exactly the same time, right? And so this entanglement works across vast distances. And this is something that really confused a lot of people early on in these experiments. When how can you have two items that are exactly paired no matter how far the distance is? So that's that spooky action at a distance. Interference, again, when we talked about what does a quantum computer look like, interference was something that can actually hurt a quantum machine because it can actually push against the forces and give you bad readings. But we also use interference for computing. So you create an algorithm in computing that can push interference so that it amplifies correct answers and cancels wrong ones. So if you're familiar with wireless signals and signal propagation, if we have two signals that are complementary, they amplify. If we have two signals that are negative of each other, they cancel each other out. And so if we can insert the correct algorithms and use the correct quantum logic gates, we can use those qubits to our advantage and create computations. And again, the last one is the wave function collapse. That's when you smack the coin down and read it. Your qubits are in multiple states at once. The only time that they pick a side is when you look at them. Observing a quantum function collapses the wave function and gives you an output. And so that's how quantum computing works. It gives us some ability to look at probability and things like that. Now that we kind of understand the difference between quantum computing and classical computing, what are the use cases for it, right? And we kind of know some of them, but quantum computers aren't good for they're not going to replace general processors, right? It's kind of like the same thing of graphic processors, which a lot of people are using obviously for gaming, but now it's a big thing for AI and data center workloads. But they are different than a CPU or a core processor, right? They do different things, and it's the same thing with quantum computers. They don't make math faster. A quantum computer can't tell you 2 + 2 faster than any transistor-based processor today. It doesn't make math faster. It makes theoretical possibility decisions faster. So we'll talk a little bit about why that is and where that occurs. But basically, if we understand what we want the outcome to be, we can let quantum computing look at all of the possibilities of getting to that outcome because we have these qubits, and because those qubits can exist in multiple states, we get a lot more data in a single qubit, and then we can combine qubits with entanglement and get just this compounding exponential increase in computing power for when we look at patterns and things that can lead to an outcome. But again, they're in their infancy. So from an application perspective, what do they believe quantum computing is going to be good at? Life and material sciences, right? So if we understand, hey, we want to make a stronger metal, we understand the outcome. We'll put a whole bunch of matter and mixtures and things like that at a quantum computer and say, find all the different possibilities with these building blocks to create our outcome, which is a stronger metal. And so those theoretical possibilities where it's trying certain things and trying other things all at the same time, and then it's showing us the probability of here's probably the best way to create a stronger metal. Life sciences are the same way. Interestingly enough, photosynthesis in a plant uses superposition and quantum mechanics to convert light energy or photons into energy and food for plants. And so our world is made up of a lot of different things. And so understanding medicine and the building blocks of life and pharmaceutical development is going to be big with quantum computing because we can run a lot of what ifs and possibilities to get an outcome of, hey, let's look at better cancer drugs and like that. It's also really good at simulating itself, right? Because quantum systems are not so much random, but there's a lot to know about them. We can actually run simulations of quantum systems with quantum computers, and it'll show us kind of how, get some of those formulas back and advance the field. Logistics, routing, supply chain. So one of the outcomes could be we want our global, our nationwide freeway system to run better. And so what are the ways, what are the different possibilities, how do we factor in all the different possibilities and have something compute the best way to have our freeways? So logistics, routing, supply chain could be an application for quantum computing. And then finally, the big thing that we're going to be talking about for the rest of this webinar is cryptography and security. So the reason why quantum computing is even being talked about in the IT world is because of this guy. So Peter Shor is a professor at MIT, and he devised the Shor's algorithm, right? So he named it after himself. But what it does is it finds prime factors faster than classical computing. So his algorithm shows how do we insert interference into a classical computer so that its output is given a number, find all the prime factors of that string. And what a lot of people told him was, you just broke encryption, right? Asymmetrical encryption with private and public keys rely on prime factoring as its quote unquote uncrackable or hard to crack shield. So with classical computers, it would take years and years and years, and sometimes, depending on the encryption, hundreds, thousands, tens of thousands of years to crack an encrypted key. But with a cryptanalytically, oh man, I knew I'd screw that up. Cryptanalytically relevant quantum computer, or CRQC, that is something that can break encryption today in hours. So you'll see CRQC mentioned in a lot of the standards bodies, a lot of the vendors. They talk about this cryptanalytically relevant quantum computer. But the reality is a lot of people are putting effort into finding encryption algorithms that cannot be broken by a quantum computer, but a CRQC doesn't exist yet. There is no cryptanalytically relevant quantum computer today. It does not exist. So the risk right now for decrypting encrypted data isn't there. However, the United States government, a lot of the standards bodies are saying it's not a matter of if one of these computers exists, it's when. And so that's why a lot of people are looking at how do we get in front of this and what is the impact. So there's two large impacts that we're seeing in cybersecurity that we're talking to customers and vendors today. The first one is post-exfiltration data decryption. The idea is that I'm going to steal your encrypted data. I can't see it and I can't read it, but one day when there's a CRQC, I'll be able to decrypt it. Once someone starts selling and renting time with their cryptanalytically relevant quantum computer, I can take this stolen data that maybe I stole 2, 5, 10 years ago, and I'll be able to decrypt it. So we're seeing a lot of customers, and especially our federal and some of our critical infrastructure customers, looking at how do we make sure that we're protected for that. And then finally, we need to create new standards, and in order to be not immune, but resistant to quantum computing. And so until those new standards are created, until we've adopted those standards and deployed those standards, that post-exfiltration data decryption is still at risk. So The first impact isn't much of a threat once the second one is realized, but the second one is going to take a while. We'll talk about that. So we're going to talk about both of these right now, real fast here. So the call to attention, the seal now, decrypt later. The way that we've seen a lot of customers and a lot of industry and a lot of vendors look at this is old-fashioned data protection, but a little bit of a new focus. So we want to make sure that not only are we doing what we normally do for cyber resilient architectures, because we all don't like malware, we all don't like ransomware, but now there's a new threat of losing encrypted data. So understanding the biggest thing, obviously, is there's two things: interception of encrypted data, right? So data in motion. If someone can intercept it, they can't do much with it today, but tomorrow they could. And encrypted data exfiltration, or data at rest. So if you have encrypted data sitting on a drive and someone steals that drive, in the past it wasn't that big of a deal, but it could be in the future if someone is able to decrypt that drive. So the newest focus, and something that we've actually baked into our discussion with our customers, is let's make sure that we renew focus on encrypted data if you're at risk of some of these actions coming to pass. As with any, even after these quantum resilient algorithms were out there, there's still obviously a big thing for key protection, making sure that no one can get your private key, so that they don't have the ability to try to hack it, right? With a post-quantum computer. So obviously making sure that you're doing your diligence today and tomorrow for key protection, identity, making sure that the least privileged access person doesn't have access to your key infrastructure and things like that. So as part of one of the things ANM does, we do a cyber resilient architecture workshop. We've added PQC to that to say, hey, let's see if you're a risk for, and see if some of the if some of the requirements apply to you as an industry, right? So that's something that we've been discussing with customers. From a risk profile, are you at risk for stealing today, decrypting later? It depends. Again, that technology is not available yet. We don't know if it's going to be next year or 10 years from now that someone will be able to, again, rent some time on a computer. The biggest thing right now, especially when we're talking with our critical infrastructure customers, is the technology isn't going to be developed by your hacker in a garage. It's usually going to start with nation state. So the NSA, China, Russia, they're probably looking at, hey, we've got a lot of secrets, and if we can decrypt them, that would be great. So obviously that's the risk is depending on what your industry is, who you guys work with. The data can be stale by then, right? So if someone steals data and then they decrypt it 10 years from now, is it still relevant 10 years from now? Maybe you're retiring soon, and it's not a big deal. I put that in there as a joke, but obviously, again, this is a few years down the road with this decryption later, but obviously there is a call to action and attention now to make sure that your encrypted data doesn't get stolen, even if you are retiring soon. So we'll wind this down with, what do I do now? Obviously, we want to make sure that nobody's hair is on fire right now. There's not a huge thing, but we want to make sure that you guys understand where to go to get more information as this technology develops and as requirements change, because obviously keeping up with it is very hard to do with all of the other cybersecurity standards and regulations, things like that. So there are a few references out there at the end of this slide deck, which I believe we are going to be providing. I'll put some links to some of these resources. The easiest way is to Google any of these organizations and then space PQC. So DHS space PQC, NIST PQC, CISA PQC. They all kind of have their own home pages, but we'll talk about each one. So DHS, the Department of Homeland Security, they've created a roadmap to provide steps to prepare for a post-quantum world. So this is a good place to develop, to see kind of what you need to do today, what they're recommending, you do to prepare, and any actions that might come up. The National Institute of Standards and Technology, they're researching and adopting standards for quantum-resistant encryption and signatures. So if you are a company that deals a lot with cybersecurity and you want to know what they're doing as far as these standards, and you want to actually comment on those standards, they've kind of been developed. They've developed a few we'll talk about, but they're still obviously working on a lot of things. And then the Cybersecurity and Infrastructure Security Agency, or CISA, they created a post-quantum computing initiative. They've got a lot of really good resources. Again, their homepage has a lot of white papers around inventory, how to use the tools you have today in order to audit kind of what you're doing for cryptography today in your environment, things like that. But they've also been tasked by executive order to update a list of infrastructure products that use PQC standards. So as we see vendors implementing some of these new standards, CISA will actually have a website where they say, here's what is aligning to the standards. Speaking of standards, there are 3 standards that were ratified by NIST: FIPS 203, 204, and 205. 203 is a new encryption algorithm, so that is being adopted right now by things like OpenSSH. TLS 1.3 is looking at that as well. FIPS 204 is the primary standard for protecting digital signatures. So obviously encryption is at risk, but digital signatures and certificates are at risk because they also use asymmetric keys, which can be hacked by quantum computers. So 204 exists as a mechanism for protecting those digital signatures. FIPS 205 is also a standard for protecting digital signatures, but based on a different mathematical approach, and it's a backup. So they're looking at if someone starts punching holes, and as they develop these things, if someone comes back from a hacker conference and says, well, we just broke FIPS 204, we've got FIPS 205 as a backup as well. Those are the standards that we see a lot of vendors going after. Again, CISA puts this list together. As you can see, it was first published a couple of days ago. But you can see some of the product categories that they're going to be adding to that list that is PQC compliant. Today, there is nothing on it. And there's a good reason for that. It takes a while for these encryption technologies. I stole this from one of our vendor partners, but it takes a while for these vendors and developers to implement new encryption algorithms. We're about right here. Those FIPS algorithms were approved last year, or the year before, I should say. OpenSSH, OpenSSL, TLS, they're all putting them into their standards, but there's still a lot of time to go for the RFCs to be updated, for the vendors to actually put it together and to start putting it out there and getting it adopted. The Department of Homeland Security has put together this roadmap and framework of what you should do today, especially if you are somebody that might be vulnerable to post-quantum computing. Obviously, keep up to date on the latest standards. It changes. We're still in diapers on this stuff. Inventory your data sets, right? So there's a good white paper on each of these items from the Department of Homeland Security, but make sure you understand what kind of data is relevant, and then which systems are using cryptographic technologies and which ones are the most vulnerable, right? So a lot of people are still using old encryption technologies. We've gone into a few places where there's this old wireless technology that they still need to use pre-shared keys, or they still need to use WEPs or something like that. So understanding where all that stuff lives is important. Discussing those with your current and prospective vendors as far as the requirements. Auditing the supply chain, so we all know how dependent we are on the supply chain. So the things you're buying could also have encryption algorithms that are weak. And then create a priority and a plan for migration. Obviously, ANM can help. As far as working with vendors, one of the things that we hope we've done today is allow you to understand the hype versus the reality. So that way, when vendors talk to you about post-quantum computing, what that means for you, A lot of the onus is on them to make sure that they're developing products that can utilize these new encryption technologies. A lot of vendors have a published step strategy. So if you look at security vendors like Palo Alto, Zscaler, Cisco, if you just Google the vendor name and PQC, they're talking about it a lot. And so you can kind of understand their roadmap. But the differentiation is going to be through operationalization. So because they're encryption algorithms, there's really not much that's going to differentiate one vendor through another. It's about how quickly can you migrate, what's the burden on your organization to get from where you are today from an encryption standard to the next one. And then obviously for our critical infrastructure and government, adding FIPS requirements for future procurements. So making sure that if you're doing an RFP or if you're doing something like that, put PQC as one of the, hey, explain what you guys are doing. That way you guys have that checkbox to say, okay, we're making sure that we're evaluating things. And then obviously give us a call, let us know. We're happy to help. Again, one of our jobs is to make sure you're not surprised by any of this stuff. So call your local solutions architect. But again, risk is low. It's another encryption update, and we're going to see more people talking about it. So we wanted to make sure that we did this webinar so that everybody can understand when they're talking to their vendors, when they start hearing the hype, they understand what it means and what it is and what it isn't. I think we're a little over on time, so I'm going to skip this one, but there's some other cool things that we're seeing as well for quantum computing. So thank you very much for listening to my webinar. I appreciate it. Hopefully we took some of the covers off of quantum computing, what that means for cryptography and cybersecurity. Any questions, Amanda, that you see? I know it's kind of a little bit of a fuzzy topic in the beginning, so if there's any technical questions, anything that anyone's seen so far with vendors or any initiatives that anybody has today as far as we've been looking at this, or it's still pretty early?
I don't see any questions right now, but I do want to thank everyone for joining. And thank you, Troy, for discussing this topic. I know we're ahead of things, but it's better to make people not have any surprises with this. So I'm sure you guys might have some questions afterwards that you'd like to share with us. I will be sending everyone the recording. And thank you everyone for joining. Our next one for ANM Pathway Series is Resilience and Recovery with David Abbott. He's our Director of Data Center and Cloud at ANM. So please take a look out for that. We'll be sending out the registration link for that this week. So thank you everyone for joining, and thank you, Troy.
Thanks, Amanda. Bye, everybody.